Thank you.
But I think they do see you. If you approach the slide here in person, they may see you playing.
Okay. I still have to,
What you could do is to use the mouse, but then it needs you to come here.
It's a bit awkward with the mouse.
Yeah. You put the mic in
Jesus.
We have 10 minutes.
Yep.
As a time here.
Yep.
You may not be able to see it behind it.
Yeah. I will probably be at 12.
You have 4 minutes for questions.
Yes. Well, it's going to be enough. Test. 1, 2, 3.
Hello everyone. Welcome back. I hope you all had your opportunity to chat, see posters, have some coffee and a little snack. But now it's time to get back to our session, and we'll have Matthaus talking about new physics in incorporating atmospheric escape models.
1, 2, 3. Is it on? Yes. Okay. So hi everyone. Welcome back from the break. I hope you're all pumped to hear more about helium, and especially with my pompous choice of title, what is this new physics thing that I'm talking about? We are in a bit of a helium crisis, despite of what you might think from all the great detections from 2 days ago that were reported there, because more and more non-detections pop up in sub-Neptunes. Specifically, more and more non-detections pop up in sub-Neptunes where we would think there should be whopping transits. And they show nothing, and there are time variability issues, and we're slowly but surely sorting out that it's might be not just time variability that is causing those non-detections. So slowly but surely we have to ask ourselves, are we missing something in our models? And so we thought, why not go back to the drawing board and think about this a bit more carefully. So I'm gonna introduce you to, not Lagrangians, don't worry, we will not, although I'm not gonna stop you from solving hydrodynamic Lagrangian in your head. We're gonna skip that part. What I mean by that is actually I'm gonna just put in mundane, normal part pieces of physics that so far were missing in most models. And I'm just gonna put them back little by little and see what can explain non-detections. Just as a reminder, from the solar system, we know we're observing those beautiful exospheres, as we already also heard today. And when such an exosphere moves from the star. See a nice little dip, and that then, well, or in cases we don't see it. So what's happening? I use a theoretical tool, which is my own code, where I can basically plug in lots of bits of physics very flexibly in and out to test individual conditions in planets. And I'm going to just show you some results from that. So the first issue that we have to care about is how complete are the actual networks that we're simulating on, or that we're simulating the triplet line population with. From this classical paper, or now classical paper, we see that there's lots of arrows, and the whole thing looks very complicated. Unfortunately, it's not complicated enough. There is arrows missing here, the arrows back, and the arrows between those guys, and the arrows between, this guy back, for example, the purple one is also not there. So there's a few things that nature provides us with, but that were not put into the models since basically this classical paper. And when we now put them back in, this is my version of the same graph. We can kind of flick back and forth between, okay, what is now changing? We have lots of new rates popping up, and particularly this blue rate up there. It's going to play a role in depopulating those upper energy states. And the end result of that is, first of all, that once we first set our view on something better than isothermal, so when we simulate a non-isothermal atmosphere, the helium population bumps up like crazy, right, by 2 orders of magnitude. And this has already been recognized in earlier works, right? This is not our invention. But what is new now is that with those additional rates, you do get a factor 2 to 3 correction for specific stars. The more your flow is dominated by advection, the worse or the more you actually need to include those rates. And there have been a few other updates to those codes by Andrew Allen and also by Ruth Taylor, who's in the audience. So as a community, we need to be a bit careful and on the lookout for what's missing here. The second effect is fractionation. Fractionation is this inability of an outflow to lift heavy elements, right? You see the red ones, which are hydrogen atoms, they're escaping and they're leaving the helium or whichever other heavy component behind. We can, how fractionation turns up in the simulations is that velocity profiles from individual species start differing. So this is oxygen and this is hydrogen, right? And you see clearly there's a massive gap here, which then pushes the mass loss rate of oxygen to be at a level that is below that of its number density ratio with hydrogen. And particularly the ionization process, the ionization process plays a role here as well, which is not included in the standard formulation by Zanne and casting, which is very popular in use. To illustrate this, I did a simple numerical experiment here, where I just said, okay, I'm gonna keep the mass loss rate of by hydrogen constant, and then I may manipulate around my spectrum so that I only change the ion fraction of helium. And lo and behold, this classical formula will tell you, no, there's only one set helium mass loss rate for this given hydrogen mass flux, but it is actually very ionization dependent. And so you actually have to solve a photochemical code to get the correct mass loss rate. The other point I'm making is that there are very large differences between different approaches, how you simulate those outflows. If you use a single fluid approximation, then hydrogen and helium, they're sort of escaping at their slightly fractionated mutual rates. Whereas if you use a proper multi-fluid approach, you can get quite different answers. And similarly for the velocities, as we just saw before. And all in all, this can lead to the suppression of the helium line. So if I now take a HD189 analog which sits or lives at this distance here, and I just move it out from away from its star, then we see that the mass flux ratio of hydrogen and helium, it drops stronger than both 1 over d squared and 1 over d cubed, which is flux and the tides. So as the mass flux ratio drops precipitously, the helium transit is successfully suppressed in this case by fractionation. But now this was a giant planet. So now actually we're interested in explaining this whole thing for subneptunes. So where are the subneptunes? The first important piece of physics that is different from standard models, which simulate subneptune escape, is that we actually start with a molecular atmosphere in subneptunes. And the molecular atmosphere, so if you just see this mean molecular weight graph, the molecularness of the atmosphere can extend over quite a significant volume that you actually observe in transit. And that's going to impact your escape in a way that we successfully simulated in Morgan Seidel's paper, who's also here in the audience. And so this plot here, I'm plotting this in a slightly different way on the right-hand side to argue that if you overestimate the cooling, which is given here by an epsilon parameter, then you can get or reproduce the standard kind of deep transits. But if you put in...
Matthaus, sorry, can you turn the mic on, please?
I don't know. Right.
Is it green?
No.
On the top, there's a...
Sorry. Now? Yeah. 1.5 minutes, no easy. Okay, sorry. So that's a bingo card, right? The molecular outflows basically successfully suppress the transit signal. And why is that? Because I'm running out of time, I'm just going to give you the run-up. In this complicated plot, we go and look to the bottom right, where we basically see the density structure. It says pressure, but we all know pressure density, same thing. Where we see the density structures of those different atmospheres. The atomic one is very, very extended, right, naturally, because the scalar is high due to the low mean molecular weight. So that gives you a whopping transit signal. And then when you actually suppress the density that is on the line of sight, and the density on the line of sight will live here, right, because that's where the helium signal is generated, not up here. That's a bit misleading. So we have to look down here. Then you can suppress the signal. And I just want to, as last thing, again advertise Yishuan's poster, which we already have heard about before. But if you're sick and tired of hearing about hydrogen and helium escape, and you think, no man, it's all water worlds, then I got you covered. Or, well, Yishuan got you covered, and we have a poster in the corner, and I hopefully can explain it. And yeah, those are my conclusions. Please be on the lookout for rates that we're missing. If you have some physics intuition that there might be something missing, right, let's talk, because it's probably important in some region of parameter space. And then fractionation can play a role in suppressing the signals, and also the molecular nature of subneptune outflows can do that job. And with that, I'm going to give over to questions.
Michael.
Hello.
Hello.
University of Chicago. Yeah, curious about your single versus multi-fluid simulations.
Mm-hmm.
In the single fluid simulation, do you account for fractionation? Is that why the results are why are the results so different?
So basically the single fluid simulation assumes it's fully coupled. So I did not add a diffusion operator here.
Okay.
But the mean momentum that the flow has corresponds to this mass flux here. Whereas in the uncoupled simulation, when the oxygen just remains at the base, right, the hydrogen doesn't have to lift it out of the gravity well. And that's why it is quite a bit higher in its own mass flux.
Okay. So do you account for diffusion in the single fluid simulation? Probably they will be.
Yeah, so if you would now separate them out again, right? They should achieve the same limits if the diffusion operator does the same job as the multifluid simulation, which in general it cannot.
So it's related to this question for Michael. So here you're plotting the mass flux in the y-axis. If you switch it to number of particles flux instead, because that's what sets the observable, right? The number of
Yeah.
Is it that hard, or is it that big of a difference?
In this case, yes.
Do you remember
because here basically all the helium is like superfractionated, and that also means that the ions and therefore the triplet state neutrals are fractionated like crazy. But this is the HT-189, right? It's a high gravity planet. So an illustrative example.
Colin?
Me?
Yeah.
Oh, I didn't raise my hand.
Oh wait, you raised your hand,
I think
right?
Shreyas was raising his hand.
Yeah, you.
Right.
Oh no, sorry. Sorry, Shreyas.
Do you have any ideas for telling apart the reason for sub-Neptune helium suppression between molecular cooling or molecular structure related effects and metal line cooling? It seems like they sort of do similar things. And sub-Neptunes have both.
Yeah, correct. Right. I think we also have the question from Michael Zhang here, who was successfully suppressing sub-Neptune signals with metal line cooling. And I think we don't know yet which one will be the ultimate answer, but we know that the molecular nature of sub-Neptunes plays a role for all outflow simulations. So I think we should start there and then add in the line cooling.
Thank you. This is Kate Bennett. I was just curious about the additional depopulation network. You think that that's going to be equally important across all different? Is there a specific planetary environment that's going to be most important in, or will it be?
Yeah. So we saw the most dramatic changes for the M star hosts, simply because the other stellar spectra are heavily depopulating the line by photoionization, right? And then basically the photoionization outcompetes the other rates.
I don't know who raised the hand first.
Anna has her hand up for a while.
Follow-up question: have you tested this for same star, different planets?
Yeah, but how different? Different masses, or?
Like a Neptune versus a hot Jupiter.
Yeah. We did that. So that generally you see that the, do I have the plot? Sub-Neptune outflows will be, so the overall column density down here, due to the flatness of the density gradient for sub-Neptunes, can be a quite severe impediment to get XUV flux in. So generally we see that there are quite a few bands that have hard time penetrating into the envelopes. So the ion fraction is quite low for sub-Neptunes as well, due to that reason. Does that correspond with your experience?
More asking what's the relative importance of the reaction rates themselves? But
Right, okay. Thanks.
All right, we need to move on to the next talk, so please post your questions on Slack. And now we have Georgia.
Wrong direction.
Is it?
The mic is on.
That was wrong. Okay. Ooh, I think it'll stay. Okay, awesome. So, hi.
Hi, I'm Georgia Mraz. I'm a third-year PhD student at McGill University, and I'm going to be talking about what we're seeing so far in some helium detections using NERPs and HARPs. So since we've had some great introductions on helium already this week, I'll go straight into our observations. So we're using the NERPs and HARP spectrograph on the 3.6 meter ESO telescope in La Silla, Chile. This is also part of the NERPS Consortium 5-year GTO time. It's part of the work in Work Package 3, Atmospheric Characterization, which also has long-term modeling of HD 189733b. So to spoil my presentation a little bit, what we're using is we're trying to use this NERPS observations to look at that helium triplet and match it to our stellar tracers that we can see in this optical wavelength with HARPs, such as H alpha. And what we're seeing so far is we're actually starting to see this bit of a correlation between the two. But I promise I'll come back to it. Let's go through and see how we got there. So as we've heard already about HD 189733b, I'm just going to flash up some parameters that are useful for my talk so that we're all on the same page. And we can see that it's a quintessential hot Jupiter here, where we have that planetary radius on the y-axis and that period in x-axis in days. And what's interesting is we can actually plot this in terms of all the helium detections we've already seen. So again, this is planetary radius on the y-axis, planetary mass on the x, and I've highlighted HD 189733b here. So all the blue show planets that have this helium detection, and the red show non-detection so far. And what's interesting, which makes this planet so interesting, as we've heard about, is that it has over 5 years of observations already of this helium triplet. And what we're seeing is that it's actually starting to vary across the years here, where we're seeing even night-to-night variation with the same instruments. So this has been thought to already be known due to variation of the stellar activity or the stellar variability, since we know that the star is a little bit active as well. So in talking about the star, we can then look at some previous observations of looking at lines like H alpha, where we have this Colley paper in 2017, where they looked at a decade of H alpha observations. And what I'm showing here is that they've plotted the H alpha equivalent width on the x-axis and this activity indicator on the y-axis. And what they were showing is that as activity changes, so does H alpha, but there's not too much of a clear correlation. And they're looking at this H alpha also in terms of this planetary atmosphere, where it's also been seen that we might have this H alpha in the planet, or it might be due to variability in the star. Additionally, we've seen recently on the archive, just 2 weeks ago from IGRIT 2025, where they're looking at modeling this star during transit. So what they're seeing is this dark blue line during transit is a quiet star, whereas the pinkish purplish line over it is showing what the transit would look like in the star with H alpha. So we're seeing that H alpha is actually varying over the transit chord. And this was really recently on the archive just 2 weeks ago. So it's something that we really need to think about when we're doing these transmission observations of this planet. So I can jump straight into our helium detections. We have 6 simultaneous transits with NERPs and HARPs. I've listed the dates here just so we can see how far apart they are. And what I'm showing here is our planetary rest frame of all of our transits combined. So the white lines are showing those start and end of transit. The y-axis is that planetary phase, so we're moving up in time, and that x-axis is wavelength. In case you can't see it, I've highlighted it here. We can see it within the transit here in that planetary rest frame of the helium triplet. But right now I'm mapping all 6 of these transits together. So we can separate this out a bit and look at each night individually. So again, I have the same connotation where this planetary phase is on the y, this wavelength is on the x, and 2 lines show start and end of transit for that particular night. So as you can see, we're seeing transit 1 and transit 5, your eyes probably go to, where we can see those helium signals, right? If you're used to looking at these plots, you might say transits 4 and 6, also you can pretty well see that helium signal. However, if you're looking at transits 2 and 3, a little concerned, so was I. Especially when I only had 3 transits. Where you can't really pull out that helium signal that we're seeing for transits 2 and 3. So we can look at these plots a little differently and kind of suppress this into looking at that excess absorption from helium. And again, I'm showing all 6 of our transits here. And again, 1, 4, 5, and 6 look pretty clear, where I'm showing this dark blue line as showing this median of all of the transits, and that lighter blue data behind it is respective to that night. And again, transits 2 and 3 are looking a little different. We're not really seeing that clear helium in them. And one more time, we can look at this data again a little differently, where we can plot the light curves, where now that x-axis is orbital phase, and we can see that we're moving across time from left to right. So in transits like transit 1, transit 5, we're seeing that really nice dip in that helium. However, to point out again, transits 2 and 3, they don't show as clear of this helium signal as the others. And what's interesting to note is that if we use the rotation period of the star, we see that transits 2 and 3, the nights are actually passing in front of the same phase of the star. So those transits are occurring when passing across the same face of that star. Now, as we learned this morning, we need to take this a bit with a grain of salt because the activity cycle might be changing, as these transits are almost a year apart. But I thought it was interesting to note here. So speaking of the star, we can now switch from our NURBS observations into our HARPS observations. And note the color change, that now we're in the stellar rest frame here. So what we're looking at on the right side is now our light curves of H alpha in the stellar rest frame. As again, the x-axis is a function of time of orbital phase moving left to right. And what I'm pointing out here is that there's a little variability in all of them that we can see definitely. But again, 2 and 3 look to be the most interesting out of all of them. And what's interesting is that when I map these on a more trace plot, we're seeing that transits 2 and 3 are actually showing H alpha in emission. So these are the only two that we're seeing that are actually showing this H alpha in emission here. So what we're seeing in this trace plot is, again, we are now in the stellar rest frame. So this black dotted line is following the planetary velocity. So if H alpha were to be in the planetary rest frame, we would see it kind of following that black line. But we're seeing it pretty straight in that stellar rest frame. And they're the only two transits that we actually see this H alpha in emission. And it's corresponding to those two transits that we weren't seeing much helium in either. So this isn't the first time that we've seen H alpha mapped to helium, and specifically not in HD 189-733b either. So we've seen it in Gilly in 2020, where they had 5 different transits as well of HD 189, and they're mapping this H alpha light curve to their helium light curve as well. And what they were showing was that in transits 1 and 3, they have this pretty extreme emission in H alpha. And those can be mapped over to their helium light curves, where they saw that in one of those, in transit 1, that had that helium emission, there was a brief peak emission in helium as well. However, their other transit that had this emission feature in H alpha actually showed excess further absorption in that helium, and it deepened their helium triplet. So we've definitely seen these kind of comparisons before, and it's not the first time, noting that this is a pretty active star that could affect this helium. So we can look at our data a little bit differently as well, and I can show back up our plot that I showed in the beginning, where right now we're looking at this on the y-axis, this equivalent width of the H alpha in the stellar rest frame. And the x-axis, we're showing this equivalent width of the helium triplet in the planetary rest frame. So right now I'm mapping only the star out of transit to this planetary rest frame. And I'm seeing that as there's more variability in this stellar spectrum, in this out of transit data, I'm seeing that the helium triplet is smaller for our observations. Of course, this is preliminary, but this is what we're starting to see in our correlations. We can also then map to our previous observations that we've seen of this helium triplet in HD 189. So now I've added in the pink points over on the right that are R6 observations. So now we have almost over a decade of observations of helium triplet in HD 189, and we can still see that it is slightly varying across these, even night to night on the same instrument. So this shows that there is some tentative evidence that the stellar activity causes this variation in the helium triplet and what we're mapping. So as a brief summary, I've seen that transits 2 and 3 are showing tentative H alpha in emission, where they have the lowest helium signal in our NURBS data, whereas the other transits 1, 4, 5, and 6 do show H alpha variability, but they aren't showing it in emission. So additionally, we have some work in progress as well, where we have, additionally to the NURBS and HARPS observations, we have simultaneous Euler-Camp photometric observations. So we're working on mapping star spots that were occurring during any observations. We are also working with Eduardo and William, who have created a SOAP stellar activity fitting. But this is what we're working on right now, so I'll keep this up for any questions.
Great talk, Laura Mraz from the ASU. So my question is, you have transits with different depths, H alpha. So my question is, do you think that might be being caused by different physics mechanisms? Maybe like particles are like messing up more with the transit in one way, and another transit is being more affected by maybe like radiation or like another thing happening that's not related to that at all. It's just like from the planet somehow. Like what could be your interpretation for that?
Yeah. So what can be our interpretation of the H alpha line changing?
Like what it might be like a physical process that is different in between like the two transits that is happening in the same planet, but like maybe a CME hit the planet in another case was just like flare.
Yeah. So I'm learning a lot this week about different things that could be the cause of this as well. But one of our ideas was that the different types of stellar activities will actually affect the H alpha line differently. As we saw in Colley 2017 maps this out as well, that a flare could push this H alpha into emission, whereas something like a faculae could actually make it a little deeper. So based on the stellar activity we're seeing, it could actually change that line. So we're looking into kind of those correlations to see what could actually be the reason.
So Ethan.
Hi, great talk, super interesting. Do you think that the variability is mainly due to the variability of the outflow or the variability of what the outflow is tracing on the stellar disk? The helium line is deeper in active regions.
Yeah, that's a good question. So of course we have to investigate kind of both sides of this. But right now what I'm mapping and seeing is that it's quite possible that it's just the stellar disk that's changing. And when we're trying to observe it, it actually shows this change that could mimic something like a change in the outflow as well.
I'm going to take the chair's prerogative because I have a burning question that's eating me alive about this planet. Carminus observations, the Carminus transmission spectrum of this planet is striking because it's the absorption is very broad. Mm-hmm. Is it as broad when you observe it with NURBS? Did you make that comparison?
I have to double check the numbers, but I am seeing a pretty broad signal, especially when we're trying to fit it, that we're seeing that it is broad as well.
Yeah. Interesting. All right, so it's still broad. All right, Katie.
Yeah, thank you. I was just noticed, like, could you show the plots and the spectra of all the different helium spectra?
Oh yeah, of course. So like this one or further back?
Yeah, when it's in here, it seems like out of the helium line, there's more scatter inherently. Mm-hmm. Do you see, if you look at the broader wavelength ranges, and how do you interpret that?
Yeah, so it definitely looks much more scatter. And when I was definitely only looking at the NURBS data, I thought that it was initially probably something systematic. But I have our orbital systematics as well. Ooh, sorry, too far. So these are the orbital systematics of all 6 of our nights. And 2 and 3 are in orange and green. So especially for transit 3, if we're looking at this signal to noise ratio for the NURBS data, this is in order that we're using this helium triplet. We're seeing that it's matching, at least for transit 3, it's pretty closely matching something like transit 4 that has a pretty strong helium triplet signature, whereas transit 2, it does kind of, the seeing goes pretty high, where you have a little bit of a drop off of SNR, so we've kind of played around with removing any of them, but it didn't make too much of a difference. Yeah.
All right, Eric, is it a quick question or We're ready to go. All right, we're ready to go. Please ask on Slack and listing her again. All right. Next we have Suvrath Mahadevan.
Okay. Hi, I'm Suvrath Mahadevan. I'm at Penn State, and I'm going to talk to you today about this very intriguing object, TOI 3884b. And I'm acutely aware I'm standing between everybody and lunch, so I'll try to make it as intriguing as possible. But one of the things I want to emphasize after hearing these talks is we can only observe these things as good as our tools are. Right? We all understand this, but it's tempting sometimes to forget this also. So I want to walk through a little bit of some of the complications in this particular system with the tool that we were using, which is the Habitable telescope, the largest aperture in the continental US, 11-meter mirror, but a little weird. It's a tilted Arecibo style telescope, and I'll explain what that means. And an instrument that we built for the Habitable telescope called the Habitable Zone Planet Finder, which originally was really built for radio velocity searches for planets or M dwarfs, right? So this is the HET. You take a perfectly normal telescope and you tilt it by about 35 degrees, and then you do not let it tilt anymore. That's a static tilt, right? So this really is a tilted Arecibo design. So you can only observe a star as it's transiting across that air mass. So typically you can observe a star for an hour or 2 hours a night. Fantastic for a spectroscopic survey. When you're trying to observe a star transiting, this is less good, right? Which means that you have to figure out when that transit time intersects with the track crossing time, and usually it happens once or twice a semester, right? But you can't just go to the telescope and say, today I feel like observing this transiting planet. It won't work, right? Luckily, the whole telescope is Q scheduled, which means you don't have to show up on those days. The data just get taken for you. So it makes it a very challenging to schedule those transits, but also makes it possible to plan long-term programs, including out-of-transit observations. Yeah. Originally, HPF was really built for this goal of finding terrestrial mass planets around the nearest M dwarfs, and it actually has begun to do that. After a couple year survey, this is actually one of the detections of a planet in the habitable zone. At another conference, this would be a very interesting planet. I'm sure it's very interesting here too. But the punchline here is the instrument is actually stable enough to do a meter per second radial velocity, tease out these signals. So we don't have to worry about the point spread function or instrument stability night to night when we're looking for helium absorption signals. So we really can lean in or rely on the instrument really being very stable long term. Also, the strategy that we've been using for some of the helium observations, this came out of a long-standing program that Carolyn Morley has been leading at UT for a few years. This is, we detected these tails, these leading and trailing tails in some cases of HAT-P32, also of this particular system, which is HAT-P67. We also detected helium from GJ3470, which is one of the very few M dwarfs from which we've had planets that have escaping atmospheres. So here is the system I want to talk about today, probably only the third or fourth M dwarf, which has a planet from which we're detecting helium escape. This is TOI 3884, and what got us interested in this was a transit we observed where there was this giant piece missing. We know what it is. It's a spot crossing. The intriguing thing about TOI 3884 was there was always a spot crossing, every single transit, right? So our interpretation and the interpretation of many authors who have written papers after this is that this is a polar spot or a polar spot complex, which is pretty large, and the planet is a misaligned planet, very highly misaligned, so it's a polar orbiting planet, which is crossing that star spot consecutively on every transit. The spot does evolve a little bit, and you can use the evolution of the spot and the test light curves to determine a rotation period of the star, which some authors have done. And it's about 11-day rotation period for the star and about a 4.5-day orbital period for the planet. There's also some chromatic variations in the transit, as you would expect during the spot crossing. So yeah, super Neptune, a polar orbit on M dwarf. Take all the things that Eileen talked about this morning and now twist your planet into a polar orbit and imagine those magnetic field interactions, right? So you know where this is going. Just a reminder of what the properties are: 4.5-day orbital period, a radius of about 6.43 Earth radii, a mass which is a little uncertain. You know, it's kind of a hard target to measure. V magnitude is about 15.5. J magnitude is 11.5. So both Espresso and HPF have gone at it, and actually they get a little bit different masses. So we get about 32-ish Earth masses, and Espresso is a little lower, something like 18 or 20 Earth masses. So there's still a little bit ambiguity in the mass and density of this planet. So we started observing this object actually to determine its mass, and some of the early helium observations were coincidental, I will admit. They came out of the radial velocity survey that we're conducting on this. HPF also has a sky fiber, and when we subtract the sky fiber from the science fiber, we also have some residuals that we have to play PCA games for cleaning up that, but we know how to do that. It's actually fairly clean after we remove the sky lines. So this is the helium 10A30 absorption that we see from a coad of near transit or in transit observations. You can see it's about 6.5%. It's pretty deep. The transit, and because the way we're observing this, because of the radial velocity campaign we have data both in transit but also outside transit, we see a very prominent leading tail. We see almost nothing afterwards. And we think we see that same helium absorption during the transit. This is a system in which the pre-transit tail is what is really convincing us we're seeing helium absorption. Because remember, during the transit, this thing is crossing an extremely active region. It's literally crossing that star spot. So if we only saw it there, I think it would be a difficult thing to hang our hat on that we're seeing it. But this makes it, I think, quite convincing that there is helium absorption here. There's, of course, this one outlier point where we measure emission, and that's actually consistent with stellar activity. We actually are seeing at the rest frame of the star's helium a little emission line, right? So the star is active. It has a giant polar spot. It's not surprising that it's active. So, you know, we went for the nearest M dwarf in spectral type, and we know this is wrong because, of course, the UV flux is wrong. So we need to get it increased by a factor of 10 from whatever default canonical closest match star to actually reproduce some of the helium absorption we're seeing. But I don't think anybody's surprised by this, right? It's a giant star spot in this object after all. Again, the usual degeneracy between temperature and mass loss for a Parker wind. But if we actually do the usual things about looking at mass outflow versus temperature, if you assume about a 5,000 degree temperature, we're looking at mass loss rates about 5 times 10 to the 10 grams per second. Sort of not again, terribly discrepant with things that have been discussed at this conference. So why do we see this outflow only before the transit? In Gulli-Santiago, another HPF result, the interpretation was perhaps we're actually launching this cold wind from the day side as you irradiate the day side. And that cold wind then follows this mass loss path and the Coriolis force twists it back. So it's possible that there's really nothing that we're seeing on the other side. So this is one interpretation we had for this particular system, but we're actually not sure how well it applies to the 3884 system. The two interpretations, again, that have been discussed at this conference are if you sort of model this as a mass loss that is either a bubble approximation or a stream approximation. If you look at where things are in Roche radius and sound speed, you expect TI 3884 to be in this regime where you would sort of interpret this more as in the stream regime, but that's kind of inconsistent with what we're seeing with only one side of the tail. But again, remember HAT P67 is also roughly there. So there's certainly some things about these systems that we are not fully understanding. So 3884, super Neptune on a polar orbit, extreme. I mean, well, not extreme. We've seen things deeper, but 6.5%, 6.8% absorption in helium shows variability from one transit to another. for sure. We don't know if that variability is helium or because of how it's crossing the spot. The EUV has to probably come from the active regions. And typically EUV for an active MROF would be enough to drive this system. Pre-transit signal with no post-transit signal, we don't have a fantastic explanation for this. So if people want to chat about this, I'm all ears. Cold day-side only outflow could power this. But the star is really standing in for what about magnetic fields? And maybe we need MHD. If people would pay me off for bingo, I needed to say that. Yeah, I just wanted to talk about this very intriguing system, one of the few M-dwarf planets for which we've measured outflow. And also in some ways, it could be a Rosetta Stone because of the interplay of activity and a low-mass planet and these outflows, which really help us to probe together all the things that are happening in this system. Thanks.
We have a question online. Roman, do you want to ask in the mic, or should I read your question?
Yes, sure, I can ask a question. Thanks a lot, Suvrath. It was a great talk. On the partial phase curve that you show for TI 3884, there's one point after transit which has a similar absorption to your pre-transit absorption level, the point A, I think it was called. However, you say there's no detections after transits because you have other no absorption points, but how can you say that your point A is not a fluctuation like this point after transits?
Yeah, so there's one, let's maybe go back to that plot. So so you're talking about this point here, right?
I guess so. I can see the laser pointer, but I guess it's the blue point on the right.
Yeah, so that point actually has a fairly large error bar because its signal to noise was quite low. So we're not interpreting that as a transit signal because we can't confidently say anything about that point.
Okay, thanks.
Yeah.
All right. Jess first.
Very exciting. Do you see any evolution in the radial velocity of the absorption?
No, not that we can tell. I think we'll probably need more data for that, another bingo thing, but not that we can tell.
It seems slightly redshifted, is that right?
Yes, yeah.
Peter. Yeah, great talk. Have you done the Russell McLaughlin to confirm that this on the phone? For anyone else?
J of almost 12. V of 15 and a half. The signal would be quite small. And the spot would really complicate this. We have thought about trying, but we have not actually done it. So.
Alina.
Interested about the polar spot. Rotation period of this star.
Yeah, so the rotation period, and this was, I think, work by Patrick Tamburro et al., is about 11 days. 11 days. Yes. Yeah. Yes. Yeah. This threw us for a while, actually. You know, we were measuring a effective V sin I, which was quite small, inconsistent with the fast rotator, and that threw us for a while till some of these papers came out that measured the rotation period. There is a question of, you know, is the planet actually inducing something on the star as well. We do measure a magnetic field just from Zeeman intensification of the titanium multiplets. There is at least a few kilogauss magnetic field with a large filling factor. So I mean, essentially we see the spots in the lines, right? So it's definitely there. So.
All right, if there's any further questions, we can ask on Slack, and let's thank Suvrath again. And I think with that, we're ready for lunch, and I'll see you all at 1:15 for a poster session.
If you are studying one about the problem child.
Was it?